All four-stroke petrol engines work following the same basic principle. An air-fuel mixture is ignited within the cylinder. This causes the piston to move downwards, transferring the power via the conrod to the crankshaft. For efficient combustion, it's important to control the gas exchange precisely. This is done by opening and closing the inlet and exhaust valves at very specific times. The piston has moved to top dead center. The inlet valves open. The intake stroke starts and fresh air is drawn in. The inlet valves close once the piston has reached the area of bottom dead center. Now the inlet and exhaust valves are closed for the compression stroke and power stroke. Shortly before the piston reaches bottom dead center during the power stroke, the exhaust valves will open. The piston pushes the combustion gases into the exhaust system. The exhaust valves will close after the piston has passed upper dead center, while the inlet valves have already reopened for a new working cycle to begin. The combustion cycles developed by Miller and Atkinson both optimize the standard four-stroke combustion process. Volkswagen initially applied the Miller combustion cycle, which was patented by Ralph Miller in 1947. It significantly increases the efficiency of a 1.5-litre 96 kilowatt TSI engine, for example. During this process, the inlet valves already close long before bottom dead center. The cylinder then contains the precise mixture quantity needed for the required torque. And this is what happens in the cylinder. The air-fuel mixture enclosed in the cylinder expands on the piston's way to bottom dead center and thus cools down. The cooling allows for increasing the compression ratio. This results in an increased combustion pressure, which allows the fuel to be combusted more effectively. The thermal efficiency of the engine increases. During the Miller combustion process, there's very little time available to fill the cylinder. Therefore, the throttle valve is opened as far as possible. The throttle losses are reduced, which is another gain in efficiency. Despite the higher compression ratio, the compression end temperature is similar to that of a comparable engine with a lower compression ratio. This reduces the engine's tendency to knock. The resulting higher thermal efficiency also leads to lower exhaust gas temperatures, meaning an exhaust gas turbocharger with variable turbine geometry can be used. Even at low engine speeds, the VTG charger generates a high charge pressure and ensures the engine is supplied with enough air despite the short inlet valve opening times. However, higher charge pressures also increase the temperature of the charge air. Therefore, a charge air cooler with higher efficiency is used. The Miller combustion process is thus very well suited to charged engines. Just like the Miller combustion cycle, the Atkinson combustion cycle increases engine efficiency. In 1886, James Atkinson had already developed this process where, in contrast to Miller's cycle, the inlet valves are closed significantly after bottom dead center. This means a fuel-air mixture is drawn in during the entire induction stroke. With the beginning of the compression stroke, surplus mixture will be pushed back into the intake manifold, just enough for the amount left in the cylinder to precisely match the required torque. For this reason, the Atkinson combustion process is very well suited to aspirated engines. Due to the delayed start of compression, the compression end temperature is, despite the higher compression ratio, similar to that of a comparable petrol engine with a lower compression ratio. The advantages of the two combustion cycles in brief: increased compression ratio, reduced throttle losses, increased efficiency, reduced fuel consumption and exhaust emissions. The Atkinson and Miller combustion processes both increase engine efficiency. The inlet valves are closed extremely early or late. This type of valve timing is not applied in standard four-stroke engines. Therefore, to ensure the cylinder is properly filled, the valve timing must be set correctly. If the valve timing in engines with these two combustion processes is not set correctly, the consequences will be far worse than in conventional engines. This is due to the very high piston speed when the valves close very early or very late. If the valve timing deviates too far from the nominal valve timing values, this will have a crucial effect on the cylinder filling. So make sure to always set the valve timing in service correctly.